Welcome to another session. In this exercise, we're going to combine two different things. We're going to look at graph mappers and we're going to do logic operators to get this sort of randomized panel distribution on NURB surfaces. So this is going to be a two-part exercise. In the first part, we're going to look at how we can model this type of twisting shape using graph mapper. And in the second part, we're going to divide the surface into strips and look at filtering mechanisms using logic operations and Boolean lists. So I'm going to start by, let's actually hide this. We're going to start by doing a series of points. And these points are going to go in the vertical direction. So I'm going to define some number sliders first. And let's feed these in and get some x, y, z points going. So I'm going to construct point. These are going to set my z values. And we want, we can actually have 10 numbers and the interval, let's set it up to be 5. So these are the points on which we're going to define some polygons. So the polygons are basically, they can have different numbers, and by default it comes in with radius of 3 and 6 numbers of segments. So it's basically a hexagon, and we can also round the corners. For this exercise though, I'm going to keep them as polygons so that we can do a lot more simpler execution. So the first thing I want to do is we can actually feed in some values for these as well. So let's say we increase the radii and we increase the number of segments. I'm actually going to decrease the radii. If I loft these polygons, you can see we're getting a straight up column. But my intention is to actually control kind of the twist of the shape. So I'm going to rotate these polygons on their construction planes. So to do that, I'm going to use something called graph mapper. Graph mapper is located under input graph mapper, and what it does is it works like a mathematical function. Basically, if I have a linear graph, which is an x equals y graph, basically, here we're looking at two different sets of values. So my x-axis is going between 0 and 1, and my y-axis is going between 0 and 1 as well. So the graph mapper takes in values in x direction, so I need to feed in a value between 0 and 1 to get a corresponding value in y. So to highlight what this means, if I were to feed in 0.25, you can see this red line forming up on the graph, and that red line is where the graph is evaluated. So if I create an output as well, because the graph is x equals y, you can see that the input is coming as output. But if I change the graph shape, you can see the output value is changing. I can also feed in a different type of graph. So let's say we work with Bezier. So you can see now my evaluation is a bit more different, and the values here are going up really fast. So because we have 10 values for the polygons, I can feed in 10 values between 0 and 1 to get this type of twisting rotation going. And for that we can use something called range. Range is similar to series. Series is basically kind of gives you incremental data, so it has starting value, step size, and total number of values. Range does something similar, but it does it within a domain. So the domain for now is set to 0 and 1, which is what the graph mapper needs, and we feed in 10 numbers of steps and it gives me 11 values. So the problem here is the series, we can constrain the total number of values. Here the range divides a domain, so it gives us always one value more. So we can fix this issue by quickly subtracting 1 from the number 10 here, so that if I feed in 9 values here, the range will give me 10. So I'm feeding it here, and these are the values that the graph outputs. So if I expand this, we can actually get multiple evaluations from the graph mapper as well. The way I often use Grasshopper is as percentage, because the y values are between 0 and 1, so they can correspond to percentages. And we can multiply this percentage with the rotation value that we want to implement. So we can say that I want to rotate, I want the rotation values up to 180. So this will give me kind of the angle of rotation for each polygon on their corresponding plane. And I can then do convert this into radians, and this will give me basically the radian value for rotation. And the rotation is basically rotate an object in a plane, so that's we can rotate the polygons on their corresponding planes. So if I use this, it takes in a geometry for that we want to rotate, which is the polygon. The angle of rotation is here, which is in radians, and then rotation plane is set to x and y, which works for all of these. We can also set up an xy plane here, which is a bit redundant, but it always makes sure that the object is rotated right. And when I feed this in, you can see now the shape that we get is a lot more dynamic. So it's not a simple extrusion anymore, it's actually a twisting shape. So if I bake it, you can see the twist, and I can control how we want it to twist here as well. Another thing we can do is control the radius value for the polygons, and that's actually a lot simpler than you think. All we have to do is just make a copy of this portion of the script, including the graph and the multiplication, copy and paste it, and change this value, because this is now, we're going to use the same percentage interpolation, but we're going to map it onto the radius value for the polygons. So if I feed this in for the radius, you can see now this is almost kind of a direct mapping of the radius values, or the section of the column. And I can increase this. The interval is a bit too much, so let's set it up, limit it to 20, so that we can see a lot more variation here. One last thing we can do is, this is kind of a regular shape, but let's say that we want different shapes for the polygon. So rather than feeding in 10 number of segments, maybe we want different numbers of segments for each plane. And that one we can also use a graph mapper, by the way, but we can also do a random. Random basically takes in a domain, takes in the amount of number values we want to create, and a seed for random calculation. So the domain, we can actually construct one manually. So if you do construct domain, a domain is basically an interval, so we need a small value and a large value. Let's say the small value, we don't want polygons less than pentagons, so 5-edged polygons, and then the maximum values, let's say we want all the way up to 12, and this goes to range. And I had 10 planes, so I'm going to ask for 10 random values. And the output here will be a floating value, so I need to convert these to integers. So if I double click here and type in integer, so these are the integer values, and if I feed this in to the number of segments, you can see it's a different type of shape. And we can also play around with the seed values, so you can see it's generating a lot of different shapes for the column. It's also controlling the radius here. We can also control the twisting here as well. So I'm going to bake this for comparison, but you can see it's a lot more dramatic. So it's kind of doing all kinds of motion. So this is essentially how we can work with GraphMapper. It's basically a straight up interpolation for the numeric intervals that you define. And in the next part, I'm going to do kind of go through these surfaces that we have. I'm actually going to first take out the limit the polygons to 12. Let's say we want to have all the way up to 12. So I'm kind of taking out the random, so the shape is a lot more straight up. And we're going to divide each individual strip into subsurfaces and do some sort of filtering mechanism. And for this one, we can start by deconstructing the boundary representation that we have. So I'm going to do deconstruct brep, and as you can see that when I bake this shape, if I explode it, basically deconstruction does exactly the same thing. We're getting individual strips because we are lofting polygons. This is actually giving us individual strips of data. And I can actually get these surfaces here. Those are untrimmed surfaces in faces of the brep. And what I want to do is divide those surfaces into subsurfaces. So that one we can actually do by using divide domain squared and isotrim. Isotrim extracts an isoparametric subset of a surface. So we need to know the domain of the surface first, and divide domain squared actually divides that domain into subsets. So if I get the surface, for instance, actually let me spend some time on this. So what do I mean by subsets and parametric surfaces? So if I have a surface, and let's actually write some text here. So we have a bottom left corner that is 0, 0, and a right top corner as 1, 1, right? So let's say this is my surface. It can be the opposite way as well, doesn't matter. And let's actually look at this. So we have two different directions. So we have this direction and this direction, and one of these is the u direction. It's like an x and y grid actually. So let's say this is the u direction, and let's say this is the y direction. So by default, these two values, 0, 0 and 1, 1, they correspond to u and v. So sorry, this was going to be v. So here, this corner would be this is u and v, this corner will be 0 and 1, because here u is still 0, but v will become 1. And in the top right corner, it will be the opposite, right? So the u would be maxed out, which is 1, and v will stay as 0. Now the point is, if I were to extract some sort of subset of this surface, let's say I want to get a portion here, right? And that portion, we actually need to know what its corresponding u values and what its corresponding v values are. And those can be some sort of floating values. And for that one, all you need to do is know the two values here. So I need to know the value on this corner, and I need to know the value on this corner. And those values will be between 0 and 1. So let's assume this one is 0.2, comma 0.22, right? So the u value is 0.2, v value is 0.22. And for this one, it's closer to 0.5, so I'm going to say 0.5, comma 0.6. Right, so if I feed in these two values, basically I can extract this portion of the surface. And this is essentially how you can divide a parametric surface into subsets or subsurfaces, because all I have to do is find out what these division intervals for the u and v values are. And that's actually what we're going to do here. So imagine this vertical strip of surface having a domain that goes from two values, from 0, 0 to some value. And what we are doing is basically we are extracting that base domain from the surfaces. So if you look here, you can see the u values go from 0 to 51, and the v values go from -3 to 0, -43 to -39. So there are different types of base domains for these surfaces. But the divide domain squared divides these domains automatically. So I can also right click here and do reparameterize, and what that does is it sets their domains to be between 0 and 1. And all I have to do is now set some numeric sliders here feed it for U and V. I'm actually going to keep them small for now because I want to find out which direction U is going, and feed this in here. And you can see that the division, individual segments, this is a grafted data because I have 12 segments and each of them is further divided up, so it gives me lists within lists. And I need grafted data coming in the opposite direction as well. So if I right click here, I need this to be grafted. So now it is actually giving me strips going in the opposite direction. So this V value is probably going in the horizontal direction, so I'm going to increase the other value. Let's make this all the way up to 20. So I'm going to turn these off, so you can see this value now controls how many vertical divisions we can have for these panels, and those panels are all here. So if I come in to the segments, what the divide domain square does, actually I will show you in a plane, in a panel, you can see that it takes in the base domain that was going from 0 to 1, and it gives me the isoparametric intervals for these subsurfaces. So it's basically giving me the black surface that I defined here. It's basically giving that to me in a series so that it divides the whole surface up. And I kept V values as 1, so what it's doing is it's actually V values are constant, so it's taking the U direction, and it's just I'll actually do it like this. So it's actually dividing this up. Let's see, 20. X is, let's say 17, Z is 1, so it's actually X is 17, Z is 1, Z is 1. It's actually dividing this whole surface up in this direction because V is 1 in my case, and it's dividing it in this direction, right? So that's essentially what we are seeing here. And in the next part, basically we have to do is look at the area values. So I look up the area values for these subsurfaces, and we don't need the clustered data here anymore, so I can right click and flatten this list out so we can get all the area values. And I'm going to look up some average value so that we can use that for filtering. So the arithmetic mean is 7.12, and we want to find out which surfaces are smaller than the average. And that one we can do if you go to math operators. Here we have some mathematical functions, but we have some logic operators too, like larger and smaller than. So if I want to find the larger values from the average value, all I have to do is feed in the areas to A and average value to B, and this will check if A is greater than B, and it will give me a Boolean value. A Boolean value is either true or false, and we can actually check if this is working. So if you go over to the area, the first area is 5.04, which is smaller than 7.12, so it's giving me false, which is basically what the Boolean check does. And we can use this Boolean list to filter the surfaces that we have. So if I do call pattern is located under sets, sequence, call pattern. It basically takes in a list and filters it with a pattern. So I can get the subsurface list, feed it into my list, and I can feed in my pattern. And we can actually get the filtered surfaces. So these are the surfaces that have areas above average, right? And I can do the opposite as well. So if I do smaller and get the area values and compare them with the average value, I can also get the smaller surfaces as well. So these two correspond to all the surfaces, but what I have done is filtering them. We can also do further filtering, so you can also take the subset of surfaces that you have filtered and do another average calculation, smaller and larger than it, so you can keep splitting these up into groups of 2. So that's another possibility. For this exercise though, what we're going to do is take these surfaces and we're going to scale those surfaces down. So we're going to create some holes in them. So I take these as is, and then we're going to get their area value again, and I'm going to do scale, and I want to extract their wireframe. So I want to get the surfaces, extract their wireframe, and the wireframes will give me all the individual edges, and we can do join curves. And we want to scale these curves, which are the geometry. Center of scaling will be the area, but you can see that we also need to flatten this list, because you can either flatten this or craft areas, which basically will do the same thing. And I can feed in some value between 0 and 1 here to control how we want to scale these down. We can also use the area values automatically. So if it's a large surface, we want it to maybe automatically scale down more. So when I'm looking at the areas, we can actually do some bounds. So look at the interval. So the area values are between 7.5 and 10.45. So we can actually divide. We can do division. We want to divide all the area values, let's say, by 12. If I feed this in as the factor, now the larger surfaces would actually scale down a lot more, right? So that's sorry, the smaller ones will scale down a lot more, the larger ones will scale down a lot less. So that will give me kind of a parametric interpolation for the surface scaling as well. So these we need to convert into surfaces again. So we can do is B function. So here I had the original surfaces, original edge curves, which I can feed in here. And these are the scaled versions, which I can feed in here. And what we want to do is couple these up. So weaving takes in a pattern and it kind of combines data. So if this data is grafted in both streams, it will actually make them into clusters. So my patterned data would become clusters of 2. And if I do a simple loft, now those will become hollowed out panels. So I can turn this off and turn the surfaces off. You can see now that part is hollowed out. So if I were to basically change the overall topology, we can actually do this in 2 ways. So I can disable this part of the script and preview the lofted surface. We can actually do a lot of tests, so we can change the input. Let's say we want to have a shape like this, and then I can enable the B-rep. Now you can see it's basically hollowing out the top and the bottom portion, right? So that's the surfaces. Oh, I actually forgot to join them at the end. So these were the unfiltered surfaces. So what we can do is B-rep join, and I can feed in the lofted surfaces, flatten that list out, and hold shift and feed in the other surfaces. So the end result will be one combined surface, which is here. So that's essentially what I got. One last thing I'm going to do is make this a bit more dramatic, because remember we had random segments as well. So maybe we could do something similar. So here, rather than feeding in the same integers, let's actually again disable this part. Let's look at the loft. So here, let's feed in 8. You can see we're having a lot of different movements. And I'm going to enable it here, but let's actually change the shape as well. Again, if this guy's like this guy's rotation is different. Let's increase this one. We can also use a different type of graph for rotation, but it's going to shift a lot, so maybe keep this as is. Now it's like a bottle, and right click and enable this portion. Now you can see the hollowed out portions are distributed in a different way, because the randomization of the radii, it's basically causing a different type of distribution. let me actually make one more. I'm doing this in 2 steps because sometimes this part of the calculation, because we have too many panels, it might give you some errors, so you might want to actually be careful. So let's see, let's make it like this. You can actually increase this a lot more so that it's more dramatic. Maybe it's like that. Okay. And the rotation, maybe we make it a lot less as well. You can also increase these values. So let's make this 12. This one is 20. So we have a lot more shapes now. And here there are going to be really small ones. I'm expecting these to open up. And there it is. So if I were to bake this, you can see that guy, these shapes are opening up a lot more, so they're on top. And here I'm getting kind of a smoothed out shape. So it's these are the surfaces that have values that are above the threshold, right? So that's why they're opening up that much. I can also increase this division. Actually, let's look at the interval. The maximum is beyond 12, so we should make this as 15. That would be actually more correct. I think the scaling was further up, so that's more correct probably. Yeah, these are bringing out more balanced panels. So that's it for this tutorial, and let me actually recap what we have done. We first developed a shape that we can twist using the graph mapper. We did use the graph mapper for 2 things, for rotation and for the radius of the polygons. And initially the number of segments for the polygons were uniform, but then I made them randomized using this random function and defined a custom domain for them. Once I get the lofted shape, then we divided up individual strips into subsurfaces, and that's done with using isotrim and divide domain squared. And we basically use these custom UNV values, and at the end I got all the surfaces, calculated their area, calculated their average, and did a larger and smaller than filtering, and I did the call pattern. So the call pattern takes in a filtering list, which is false and true and false, and then you filter a list, and then I got the wireframes of individual polygons, joined them, lofted them into panels, and then joined it with the filtered surfaces. And basically the surfaces, NURB surfaces, when you're looking at their domain, if they're normalized, they go from 0, 0 to 1, 1. And when we want to divide these up, we are actually dividing the UNV parameters and defining the isoparametric interval for these subsurfaces, right? So that's how we are actually getting these subsurface divisions, and then calculating their areas and scaling them down. So that was basically the essence of this exercise, and so that's it for this week. I'll see you next week with some more tools.